If you have different aldehydes, you can do a crossed aldol reaction or a mixed aldol reaction. If I were to put acetaldehyde plus this propanal into a reaction flask with sodium hydroxide, I'm going to get a big mixture of things. And I'll try to keep the colors straight here so that you can see what is coming from what. This one can form the enol, so you can be reacting this aldehyde plus this enolate. That would give you this OH that was being attacked. This is the original aldehyde, and that's the new bond that would form between them. You could react two of these molecules together, so you'd have this aldehyde plus this enolate. So you have this, and then the original aldehyde. This new bond would form between them. You could have acetaldehyde, this as the enolate. So the enolate is going to form a new bond there, which will attack the aldehyde. Or you have this one acting as the electrophile. This is the enolate. New bond. So this is a very large mess. Just from these two different aldehydes in one reaction mixture, you're going to get 4 different products. If you want to control the products, there is a way to do that. There's 2 methods to doing that. One method is to use formaldehyde, where there's no extra alpha protons. If you do this, this is going to be the one with the enolate, because this one has the alpha proton. So you have this aldehyde, we make a new bond to formaldehyde. So that is one method, is to do it with no alpha protons. So that's one method, is to use formaldehyde, which has no alpha protons, or something like benzaldehyde, which also has no alpha protons. So you have the aldehyde, new bond. This actually is not isolated. It will go right to the alpha beta unsaturated product. The second method for trying to control these reactions is to add the reagents one at a time. So LDA is a good base to use. That's lithium diisopropylamide, which I believe we saw earlier in the chapter. We add LDA to form the enolate first. And then we're going to add the carbonyl to that. So once we form all of the enolate with this, these ions in solution are usually red or orange in color when they form the ion. So once you form the ion, that enolate can then attack this carbonyl. So that's my acetaldehyde. I form a new bond. And that's the propanal that gets added to there. So that's the second way to control the reaction. So here you want to describe a synthesis using alpha carbon chemistry and any other reactions to yield the following compounds. So all we're asked to do is to do something with alpha carbon chemistry. We can pinpoint where the alpha position is. There's one here and there's one here. This one's probably easier to get at because it only has the one substitution. And what you can recognize here is there's an alpha beta unsaturated carbonyl. And those come from aldol condensations. If you remember how we put those together, you can kind of dissect this. So that one, we're going to do the retro here, came from this alpha carbon. So that's the carbon that stays there. This is the alpha. And then if we cleave this, that came from this right there. So if you remember when we did the aldol condensation, you drew the original ketone or carbonyl and made a new bond to this. This is where the new bond was being formed, and we just lopped off this oxygen and kind of shimmied that up over there. So that would be the reverse of that. So to do this reaction, this is going to be the enolate. So LDA. That will make the negative charge there. And then to that, I will add this aldol, followed by acid and heat. You could also use base and heat there. So that's my original ketone. You draw your new bond here, and then I had 2 extra carbons. So that's how we would get to that product. We can form cyclic compounds also through intramolecular aldol reactions, and these you would just draw the mechanism inside. So the product that we would form here, one of these is going to get lopped and then kind of connects to the alpha position here. So if I'm drawing that, I have, this is 2, this is 1, I have 3, 4, 5. So I'm going to make a 5-membered ring. This is 5, and at 5 I have a methyl group. And the new bond is going to occur between 1 and 5. So there's a double bond here. So I'm going to redraw that quick because this is kind of sloppy. 1, 2, 3, 4, 5, and the new bond forms there. Okay, it's still not the prettiest, but you get the idea there. So we had an intramolecular reaction. The sodium hydroxide would pull off this proton at carbon 1, form the enolate, which can then attack the carbonyl within itself. So you can see this nucleophilic site here from the enolate and the electrophilic site there. So 5 and 6-membered rings are likely to form. Esters can also go reversible condensation reactions. In this case, we have ethoxide, which is going to be the base. Typically, you want to do a Claisen condensation with the ethoxy that matches the ester part. So this is OET, so we use OET minus. So this OET minus is going to grab this hydrogen. We're going to form the enolate. There's a negative charge there. So this enolate will attack the ester, which is a good electrophile. Those electrons will go up there. So I have original ester, new bond, second ester, so there's my tetrahedral intermediate. If we can form a double bond from carbon to oxygen and have a leaving group leave, that's going to leave, so that gets kicked off. So I have original ester, the new bond that was formed. So that ester left, so I have minus OET and a new carbonyl here. This is alpha beta. So the product is a beta keto ester. So you can see the ketone is beta to the ester, and that's why it's a beta keto ester. All right, so at the end of the day, you're going to make this. So when you're drawing the product, you can go through the mechanism. You have the shortcut. This is the original ester. You draw the new bond coming off of the alpha carbon, and then this part of the molecule here that is circled is what gets added. So this C double bond O and that methyl group. Okay, there are some limitations to the Claisen condensation. The starting ester has to have 2 alpha protons because removal of the second proton by the alkoxide is what drives the equilibrium forward. The hydroxide cannot be used as the base to promote Claisens because you could get a hydrolysis, which is why we use the equivalent alkoxide to the OR group of the ester. That way we also avoid trans-esterification. We can do cross-Claisen condensations using the same strategies as the aldol. So here there's no alpha protons. This one has 1. So when you're drawing your product, the one with the alpha protons is going to be the nucleophile. So that's the one that you draw first. draw a new bond, and then everything except for the OR is going to get added. So that would be your product there. That's the method where there's no alpha protons. If you're going to mix them together, or you form the enolate first and then add the second ester. So we'll draw our original ester, new bond, and then everything but the OR. And just like aldol condensations that we could do cyclic ones, we can also do cyclic Claisen condensations. If it's an intramolecular Claisen, this is called a Decmanization cyclization. 5 and 6 membered rings are preferred. So in this one here we have 1, 2, 3, 4, 5, 6. This is a diester. 2 is where the alpha site is, and that's where the nucleophile is going to form. And so we're going to get a bond between 2 and 3. So this ester part of it, this is not in the ring. So the bond is going to occur between 2 and 6. So I'm going to start with 1 over here. This is 1, this is 2. So if I have a bond between 2 and 6, I have a 1, 2, 3, 4, 5 membered ring. So I'm going to prepare to draw that. So this is 3, 4, 5, 6. The new bond forms here, and that will be ketone. So you get the beta keto ester. This is 80%. All right, what reagents would we need to synthesize the following? We're going to look for the original ester with an alpha carbon. This one is making a 6-membered ring. This is probably the new bond that was formed there. This is a beta keto ester. So this is my original ester. So I'm going to have 6, 5, 4, 3, 2, 0. Didn't think that one out there when I started numbering. So this is 6, this is 5, 4, 3, 2, 1, has 2 methyl groups. And then this will be the ester there. And that one is 0. This one is not forming a cyclic ring where the ester is inside here. The new bond is occurring right here. So this would come from this ester. And the other molecule would be this ester right here. Aside from doing Claisen reactions and aldol reactions, we can also alkylate the alpha position. So we can make new carbon-carbon bonds by forming an enolate and then treating it with an alkyl halide. Once we react a ketone with LDA, that's going to form a negative charge there. So that's our enolate. And then we add our RX, where X is a leaving group. Enolate can attack the R and kick off the X. So we have a new bond, and we've added the R there. So there's a possibility to do an SN2 reaction here. If you use a secondary or tertiary alkyl halide, the enolate can act as base in an E2 reaction. So you want to keep this to primary alkyl halides. When you're using LDA, you have the option of 2 different alpha protons that can be abstracted. So you want to keep in mind that if your molecule is not symmetric, you could have a mixture of products there. So regioselectivity is an issue when you're forming enolates. One way to get around that is to use different bases, just like we use T-butoxide versus DBU to control the elimination product. If you have a substituted alpha proton here, so there's an R group here, one base will give you this kinetic enolate. Less substituted, less stable. This is the one that will form quickly. If you want the thermodynamic one, this is the more substituted one. If you want the kinetic enolate, and add to the less substituted carbon, this will happen quickly, and so you don't want to give it the opportunity or the energy to do so. So this one usually you will do under cold conditions. If you want the more stable product, that has a higher activation energy, so you need to apply heat to that and give it more time to react. So this was going to be warm conditions. If you have a warm situation, this is thermodynamic. So the new carbon bond will form at the more substituted position. So you have that R and the addition of a second R. At minus 78 degrees, the substitution will occur at the less substituted carbon. We also look at the base that is used. Lithium diisopropylamide is a stronger base. So that will also react quickly and irreversibly. NaH is not as strong. And can be reversible with heat. And 25 degrees is sufficient amount of heat for that to be reversible. Alright, so we want to give necessary reagents to synthesize the compound below, starting with fragments that are 5 carbons or less. So 1, 2, 3, 4, 5, 6, 7 is the chain going all the way across. So we can't just start with this big ketone here. But what I do notice is that I have carbons being added at the alpha position. The carbon chain going all the way across, we said, was 7 carbons. This one here is 1, 2, 3, 4, 5, 6. So I can't use that carbonyl either. However, I can use 1, 2, 3, 4, 5, and then I can do alkylations at the different positions here. So that'll be 1, 2. Okay, so that's the carbonyl I'm going to start with. I'm going to start on this side of the molecule. I think that will be easier. I'm going to deprotonate at this position on the more substituted, so I'm going to use NaH at 25 degrees, and I'm just adding 3 carbons here, which is circled in green. 1, 2, 3. And then I need to add 2 methyl groups to the other side, so I'm going to use LDA at minus 78 degrees Celsius. I'm going to do that one in excess, and then CH3Br in excess as well to get the 2 methyl groups. So we alkylated protons on carbonyls that were aldehydes or ketones. We can also do that with a diester where there's a hydrogen or alpha proton in between there. This will grab this proton and get a negative charge here. We can then add Rx. And you form a new bond right there. If we add acid to this equation, we can hydrolyze those esters to carboxylic acids. And you have that bond there. So this is the malonic ester synthesis. So in that, a halide, which is the Rx, can be converted into a carboxylic acid with 2 extra carbons. So halide can be converted into a carboxylic acid. If you heat up that reaction, so you have that diacid here between those, you can decarboxylate it through a pericyclic reaction. So you heat it up and you lose CO2. This is what would result from those arrows, and then it's going to tautomerize. And you get that R group right there. So you start with this specific ester. You're going to form the enolate here, which will then attack this bromine. We add acid and heat. At the end of the day, you get that alkyl halide without the Br, and you form we add 2 carbons in the process and a carboxylic acid. So you can alkylate 1 time. We can also alkylate 2 times since there's 2 alpha protons there. So we have this ester. You'd add the first R, and then there's still an acidic proton there. You then add the second R. We add acid and heat. One of these gets hydrolyzed to the carboxylic acid. The other one is lost as CO2 after it gets hydrolyzed. So you end up with that product. So in this synthesis, we don't have a diester, but we can do similar chemistry. This is going to form the enolate from the sodium methoxide ethanol, which is going to attack there. New bond. We're going to get a ketone here. So we have this carbon, that is this one right here, and with the addition of acid, this is going to get hydrolyzed. And then heat, this will get decarboxylated. So minus CO2. So we get that product.